Alright, so in this example we're going to look at a semantic segmentation problem or a pixel level classification, and we're going to work primarily in the ArcGIS tools without using a lot of code, so with minimal coding. Okay, so before we get started, I just wanted to remind you that if you are working in ArcGIS Pro, you can't just use these tools natively. You have to do some installations, at least currently. So this page, this GitHub page, explains how to do that. So if you're using Arc Pro 2.6 or 2.7, you can simply just download the files and then run this executable that downloads, and that will effectively upgrade your Python environment that installs with Arc Pro to do all the deep learning. So in short, what happens is it installs a bunch of additional tools. So things like TensorFlow, Fast.ai, PyTorch, so on and so forth, that are used to do deep learning. Okay, so it's actually easy to do. If you have an earlier version, you have to do it more manually and like clone the base environment. But I would suggest just updating your software and then using one of these installers. And currently this works on Windows and Linux, and I also believe on Mac. So I'm on a Windows machine. Another thing, again, worth noting is that you need to have access to certain hardware in order for this to work efficiently. So currently, deep learning is really done on GPUs or graphics cards, so you need to have a good graphics card. Specifically, you want to have an NVIDIA graphics card that's CUDA enabled. And you can look at what cards meet certain requirements. So they suggest here that you need an NVIDIA graphics card with a CUDA compute capability of 3.5 to 6.1 or higher. I'm currently using a machine that has an NVIDIA RTX 2080 graphics card in it, which is an 11 gigabyte graphics card, and it seems to work pretty well for this. You also need a decent amount of memory, so generally you want a graphics card with at least 8 gigs or so of RAM in it. And then here you can see all the different packages that are installed to make this work. Okay, so that's this initial. Again, if you want to see some additional documentation, you can look at the ArcGIS.Learn module book, which is online here, and this talks through all the different implementations that are available and the pre-processing and prediction tools and whatnot. We're not really going to look at this in code since we're going to do that mainly with PyTorch, but you can run a lot of the processes that we're looking at inside of Arc Pro using the ArcPy within the ArcPy environment. Okay, so before we get into actually doing the analysis, I wanted to spend some time discussing what we're actually trying to accomplish. Okay, so what I'm doing here is replicating a study that we put together about a year ago related to trying to extract information from historic topographic maps. Now, note the original study was done using TensorFlow and code, so I'm basically replicating or approximating, I guess, what we did in this paper using the ArcGIS environment here. So if you're not familiar with Topo Maps, there's a series of Topo Maps that have been developed since the late 1800s in the U.S. from the United States Geological Survey. And they can be used to look at, obviously, topography, but also old landscape conditions. So, for example, this pink fuzzy stuff represents historic surface mine disturbance, so things like surface coal mining, quarries, things like that. In West Virginia and Eastern Kentucky, where the data we're going to look at here, most of this is going to be associated with surface coal mining. So in this study, we use data from, let me go down to this map here. We use data for the eastern part of Kentucky, where there's a lot of current and historic surface coal mining, to train a semantic segmentation model, and then we use that model to make predictions in new areas to get a sense of how well it generalized to new data and new maps. Specifically, we looked at some areas in Ohio and some areas there in Virginia. Yeah, so, and then the actual architecture we used was a UNet which is, again, a type of semantic segmentation method. And here you can kind of see the features. So we have our mining, and with that specific symbology, and here we've overlaid some vector objects on top of it. So where did this data actually come from? So the USGS has been working on digitizing this. I'm going to play this video here. They've been working on digitizing the historic surface mining from old topo maps for a while now, and they're making that data available as it's finalized. You can see this progression through time. So effectively, this was the source of our input training data for our model. And you can see here that they make databases available either as geodatabases or shapefiles or KMZ files on a state-by-state basis. So currently West Virginia isn't complete, as you can see here, but Eastern Kentucky is. So we mainly use the Eastern Kentucky data in this example. So we actually went through and did some manipulation with this data and made sure we can match all the features up with a specific topo map to create our training data. And then our topo maps actually come from the USGS also. Here's a good site to go to get historic topo maps, so Topo View. If you launch this View and Download Map button, that opened up video, there's a tool here to search and download maps and whatnot. Okay, so that was the source of the input data. All right, so now we're ready to start developing our input or training data to generate our deep learning models. And again, the goal here is to try to create a model that kind of automate the extraction of these old surface mine features from topo maps. So here I brought in a topo map just so you can kind of see the structure of the data. So this is the Williamsburg Quad in Kentucky, and it's representing conditions in like 1969. Okay, so if we zoom in here, you can see that we have a good bit of mining features with that pattern, but there's also a lot of other complexity here. So we have text and forests and overlaid contour lines and labels and everything. So this is actually a fairly complex extraction process. So it seems like this would be an adequate the deep learning would be an adequate method to explore here. So luckily for us, we have all this training data, which was provided by the USGS. And again, we did some manual cleanup to make sure it matched with the topo maps. We make this data available if you want to play around with it or follow along with any of the examples. Okay, so I have 3 layers here. The first layer is a raster. So this is a raster-based scan georeference topographic map. So it includes the map itself and then also the collar information, so all the ancillary information around the sides. So if we're interested in trying to extract map features, we really don't want any of this collar information to be considered. So we also have for each topo map, and this is again just from the USGS, the boundary here, and you can see that laid out. So we have the rectangular extent of the map, and we're going to use that to get rid of the collar information since we don't want to create image chips from that. And as we already saw before, we have this vector layer representing the extent of topographic of the surface mining. All right, so one thing about your vector data that's important to know is that a lot of these tools assume that you created the training data using the training data management tools in ArcGIS Pro. But I actually didn't create them that way, so I had to kind of trick it to make it accept this data. So specifically, if we open up the attribute table, I've added a field at the back end of the table called class value, and if you hover over that, you can see there that it's a long data type, and I filled that up with just ones because there's only one class here. Either mining or not mining, right? So this class value field is a field that would be created in the training data if generated with the training data tools in ArcGIS Pro. So I added it here to basically trick it to accept this data layer. So that's kind of a key kind of workaround if you're bringing in data from a different environment. Okay, so the tool that we're actually going to use to do our training data creation is called the extract training data, data for deep learning. Okay, there we go. So it's, it's export training data for deep learning. And you can see it's cross-listed here. You can grab the tool from Image Analyst or from Spatial Analyst. It really doesn't matter. Obviously, you're going to have at least one of those licensed, right, to use it. So I'm going to just go to the Image Analyst tool, and as you can see, there's a bunch of deep learning related tools here. We're going to look at some of these as we work through through some different examples. So again, here we're just looking at this export training data tool. Okay, so let's step through this to get an understanding of what we're doing here and what all these different settings mean. Okay, so the input raster is the raster image that you're wanting to create image chips or patches from. So that's going to be our topo map. The output folder is where you want to store these image chips. So I actually created a folder here called, let's see, where are we? Topo chips, where I've ran this before. But I want to run it again from scratch. So I'm going to create a new folder, and we're going to call it just Topo Chips 2. And we'll click on that folder and hit OK. A little warning message will pop up here that tells you that the folder already exists, and that's because it can actually create these folders like on the fly. So it's just telling you it's going to override it if it already exists, but that's okay. Okay, and then we give it our features that are going to represent our masks or our features of interest. So that's going to be this layer here. So that's the boundaries. And we have to give it a class value field, and this is used to differentiate the classes. Again, here there's only one class, so we're not really differentiating anything, but we still need to provide something. So we're going to use the class value. We don't need to set a buffer radius. Sometimes this is done if you're using like line features or point features as your training data and you want to convert that into an area. But we already have aerial features, so we don't need to do that. So we'll just leave that at 0. And again, we don't want to create image chips in the caller because, again, that's not really map information. So we're going to set our quad boundary here as a mask. Okay, so that should be all the input data. Now, the next set of things relate to how it's going to generate the chips. So the first argument here, image format, is the data format. So we have TIFF, MRF, PNG, and JPEG. I'm going to use PNG. You know, they're compressed. They tend to be a little bit smaller. I also find that a lot of code environments work pretty well with those, like some of the later examples. So we'll just use PNG, but you could use TIFF or JPEG. Doesn't really matter. The tile size, X and Y, is the size of each image chip or patch. So there's some considerations here. One is kind of the scale of the data that you're working with. So you obviously want a big enough window that you can like see your features, that you're not just constantly seeing like parts of features. This is also impacted by the resolution of the grid. This grid is roughly a 2 meter by 2 meter resolution. So if we do a 256 by 256, it's like roughly a half a kilometer by half a kilometer. Or sorry, yeah, that's right, half kilometer by half a kilometer dimensions. But probably the most practical consideration is issues with memory. The larger you make these chips, the more memory it's going to be required to train the model and then do predictions. I found on this machine, which again has an RTX 2080 graphics card in it, that sometimes I can use like 512 by 512 chips. I'm generally not able to use anything bigger than that. I think for this specific task, the 256 by 256 actually makes a lot of sense. So I'm just going to leave it at the default. The stride X and stride Y settings, those relate to how far the image or the window moves over as it generates chips. So for example, if we set it to be the same as the size, 256 and 256, then you're basically going to get a bunch of chips that butt up against each other, but they don't overlap at all. Here we're using half that distance, 128 as opposed to 256, which means that each chip is going to overlap by half both the X and Y directions. So you're not just going to get, an image broken into non-overlapping chips. You're going to have overlapping areas. So there's a couple reasons why people do this. In terms of training, one of the main reasons is to generate more training data. So you can represent the same features at different positions within a local window or chip, so generate more variability and training samples. So I'm just going to leave this as set 128 by 128. If we would set it up again to 256, we'd end up with less data. If we set it down further, we'd end up with more chips. I think that's good. You can do a rotation. We don't need to worry about that. Reference system, you can either use the map space or the pixel space. We're going to leave it at map space. That means each of these chips are going to have geospatial projection, coordinate system information associated with them. So if you actually read them into your map, they're actually going to draw where they're supposed to. This is a really important setting. By default, it only is going to export chips that have the feature of interest in them. So only chips that have some mining in them will be exported. Any absence only or background chips won't be exported. For this problem, I actually think it makes more sense to try to export or use some of the no feature tiles. And that's because it would give the algorithm a chance to see more examples of not mining or background classes. So I would, if I was trying to generate a model for production or for use, I would probably turn that on. The issue here is that's going to generate a lot more chips, right? We're going to have a chip for every location with or without mining. So in this example, I'm going to not do that. I'm just going to export the mining chips, but I think that in a production sense, that would probably be better to actually export everything. But again, for the sake of time, I'm just going to leave this blank. So that's the default. And then we have metadata format, and this has to do with how the structure or format that the data will be generated in. If we hover over this, it'll tell you a little bit about all the different options. The key thing here is that you got to make sure that you match your data output type to the correct type of problem. So for example, RCNN masks are going to be useful if you're doing instance segmentation with something like mask RCNN. What we're interested in here is semantic or pixel level classification. So we can use the classify tile method. And basically what that's going to do is generate a bunch of image chips and an associated binary or multi-class mask depending on the problem. This is going to be a binary mask because we just simply have mining or not mining. So I'm going to change this from Pascal visual object classes to classified tiles. And that should basically set everything up the way that we want. And that should be it. So let's hit run and let's execute that. Okay, so this is starting now. You can see it running. Now, if I go into the folder that it's writing to, so I'm going to go into my Topo Chips 2 folder here. We can see that it's already generated some subfolders in there. The images folder is going to store your image chips. So if I open that up, you can see there's a bunch of stuff being written, and it's still counting there. So it's still working. So I'm just going to do a view, change the view here. And you can see what it's doing is it's generating all these 256 by 256 image chips. And there's some ancillary files, so for example, with the projection information and stuff. So there's all of our chips. You'll notice pretty much all these chips have at least some mining extent in them. And again, that's because we've told it not to export any chip that is background only. One thing I wish was available in Arc Pro, which I don't believe is, with this tool specifically, is if you have a lot of background chips, you might not need all of them. So it would be cool if it could export out like a subset of the image chips, or sorry, the background only chips. But as far as I know, there's no way to do that. It's either all background or none of the background. Anyway, so there's a writing there, and while it's doing that, it's also creating the master labels in another folder. These are just going to show up as black because they're just 0 and 1. It's assuming it's like a 0 to 255 stretch. So there's not really much to see here, but that's what, it's basically generating an associated mask. Okay, and then we'll give this a few more seconds. This should be done. You can see here that it generates some other files, and we're going to use some of these later on. So we've got this Esri accumulated stats file, which is in a JSON format, which is JavaScript object notation. We should be able to open that up in like a plain text editor. Let me just open it up real quick with, let's just do Notepad. So you can see the structure of it there. So it tells you it's basically storing some ancillary information here. So we have the number of bands, the tile size, the number of classes being differentiated, the class codes, and we have some statistics for the different image bands there. And we have this EMD file, which we'll use later. This map.txt file shows you the mapping between the image and its associated label. And as you can see here, it's the same file name. It's just in a different folder, right? And it just started at 0 and then worked its way up. Sometimes I've had issues before where it messes up a certain layer or file and it doesn't have associated mask. If you have that issue, you can make Python scripts that can go through and make sure the files exist and delete things if they don't have a match in the mask folder or whatever. So that can be useful. And then in the stats, it tells you a little bit about the data. So basically what we ended up with here was a total of 924 image chips. There's 3 channels made in 256 by 256 in terms of the spatial dimensions. There were a total of 1,396 different features identified across those chips. The maximum number of features per chip was 5. The lowest was 1, which that was basically just based on the definition here because we weren't exporting absence only or background only chips. So that's just some information about the data. One thing that's cool is if you wanted to, say, generate more chips and store them in the same folder, like, for example, pull in another topographic map and generate chips on top of that, you can actually write into the same folder and it'll just take off and add to this. So, you'll, instead of writing over chip 0, it'll start with wherever it left off and then add to all of your metrics and maps and whatnot. One thing that's problematic or frustrating with deep learning is that you generally do need to have a fairly large data set to get good results. So training this model on a single topo map would probably be inadequate. We'd probably want to use a large set of topo maps. Okay, so as part of our project, we generated a set of topo maps with associated masks and mining extents as vector objects. And that's this data set here. Again, we're making that available if you want to play around with any of it. Okay, so for example, in this KY mines folder, we have the shape files representing the extents of mines for a bunch of topo maps. Here are the actual topo maps. There's 122 overall. And then we have some additional maps in Ohio and in Virginia. This folder contains all of them just dumped in the same place. So overall, we have 170 topo maps. So let's say we wanted to actually generate chips from all of these collectively or a subset of them as opposed to doing them one by one. Well, that can be difficult to do with just the tool in ArcGIS Pro. So I was going to show you how we implemented that or undertook that using Python. Okay, so I'm going to open up Python environment here. So I'm going to go to my ArcGIS folder and then just open a Jupyter notebook. So this is going to open a notebook using the Python environment installed with ArcGIS Pro, which doesn't make sense in this case because we are because we want to use ArcPy and whatnot. So you see here that opens up in a web browser. So if we go down, let me find my example here. Let's look at this one. So chip prep single folder. So I'm going to open that up. Okay, and then just to make this a little bit easier for you to see, I'm going to bump the size up here. Okay, so I'm just going to step through this to show you how we did this kind of mass chip generation process. Okay, so first off, when you're using functions made available through ArcGIS, so I'm importing ArcPy. I also am using the deep learning tool, the extract training data for the deep learning tool. So I need to check out either the spatial analyst or image analyst extension. So you can see I did that there. And here I'm just importing some other things. So importing functions from the image analyst module and the spatial analyst module. I'm also importing the environments. Outside of ArcGIS, I'm importing OS for some operating system related stuff. In the next block here, I am setting the folder that houses the data. And then I'm specifying what folder contains the topo maps, the mine features as shape files, and then the masks or quad boundaries also as shape files. And then I create 2 new folders, one to store copies of the topo maps in, and then one to store out our derived image chips. So I already did this one, so I'm just going to change this to 6 and 6 there so I don't overwrite the original. And then I use this make directory method, function from the OS module to generate those 2 new folders. So first off, I'm going to run this. And if you're in the right environment and you have all your correct libraries, modules installed, that should run without any issues. Okay, so once that runs, if I run this block, it's going to go through, generate those new folders, and down here I had it print out all the topo map file names. So to do that, I set the working directory to the folder that has the topo maps in it. And then I use this list rasters function from ArcPy to list all the rasters that are in there, which again are all the topo maps, and I just printed those out. So you can see our long list of Kentucky topographic maps. So it's the full file name, but not the file path. How I matched everything up in this specific example was I gave everything the same name, so they're all the exact same name. But the topo maps are going to have a .tif extension, whereas the masks and mine boundaries are going to have the .shape extension. So to make this a little bit easier, I make a separate list here where I'm basically splitting up the paths to get rid of the file extension. So I just get back just the name. So I create an empty list object, and then I iterate through all the chips in this list as a for loop to get back just the name. And what I'm doing here, or without the extension. So extract out just the base name, and then I extract out the first component. That gets rid of the file extension, and I append that to my list. So in each iteration is going to add one feature, and then I print it. So if I run that, basically what I get back here is just the same list, but now with the file extension removed. And that's going to be what we're going to iterate over in order to generate our output on a chip-by-chip basis. Okay, so this function goes through and actually generates the chips. So again, I set up a for loop here, and effectively, again, what I'm iterating over is this list object. So I'm going to grab the first list object, work through it, grab the second one. So this is going to allow us to go through each each topo map and generate chips from it one at a time. Okay, so set a working directory to be the topo folder. I get out the quad name. I replace any spaces with underscores just in case, underscores generally any spaces can be issues, right, with some environments, like, for example, Spatial Analyst and ArcPy. I define a subdirectory where I'm going to store out the chips, and then I pull in the raster there. So the first thing I do is I convert all these images into PNG images with an 8-bit unsigned data type. So I'm copying the raster there. Once that's done, I then read in the mine features, and those are again going to be our masks that define the extent of mining. Remember that from the last video, the class value field was used to specify the class code. So just in case that doesn't exist in a file, I want to create it. So I do that using this if statement and some list comprehension. So I basically say if the class value is not in the list of field names from this training object, then add it. And then once I add it, then I calculate it. I calculate it by putting 1 in the attribute. So if it doesn't exist, it'll go through this code and basically create the field, populate with 1. If it does exist, then it won't have to do anything. Okay, so next, what it does is runs the export training data for deep learning tool. Before doing that, I define some variables. So we're going to create PNG chips. This is the size of the chip, 256 by 256. The stride, so they're going to overlap by half in both the X and Y directions. We're going to have it only export tiles with features. Again, you can change this to export all tiles, which again would probably be the better way to do it. But in this example, we're not, because we're just just for the sake of speed. We set a start index, tell it the field we're going to use to specify the class, so that's the class value field there. And we're not setting a buffer. We're setting in the input mask, and again, that's just going to be the quad mask that we came up, the quad boundary. Again, we're just getting rid of the collar or ancillary information around the margins. Export to the map space, process a mosaic image data set, don't blacken, and fixed size cropping. And then we just feed those into the function here, and that's going to generate our chips. So it'll go through each of the topo maps and do that one by one. Note that each of these chips, or each of the topo maps, all the associated chips are going to get dumped into the same folder. So it's just going to continue to index as it goes along. So we're going to get this giant data dump of chips as opposed to a bunch of separate folders. I'm not going to run this now because this takes a while. It took about a day to run since there's a lot of data here. But I did want to show you what the output was. Okay, so in this folder, I did this in this processing folder, and this is a version that I already ran. So as you can see, this generates effectively the same output that we got from running the tool separate, or the tool within Arc Pro, except now we're doing it over multiple maps. So you can see there's a fairly large folder here with tons of features in there. It's still counting. So let's just look at the stats. So if we go into stats here, we can see that it generated from these topo maps a total of 37,183 image chips. They have 3 bands, again 256 by 256 dimensions. There was a total of over 64,000 features. Anyway, so it's a much larger data set than what we got when we processed a single image or a single topo map, which is good because generally you're going to need a good bit of data to get decent results from this, for deep learning. All right, so at this point, we've now created training data from a single topo map, and then we also created a bunch of training data by using Python to iterate over a bunch of topo maps. So we have what we need to effectively train a semantic segmentation model. So again, if you wanted to do this in code, if you can look at the ArcGIS.learn module example page here and then code that out. Again, we're just going to use the tools in Arc Pro because we're going to do our code base work later, mainly just using PyTorch. Okay, so but let's just look at the tool we're going to run. So we want to train a object, or not, a pixel classification model. So I'm going to click on that, and as you can see here, there's several different options. So you have UNet, PS, PNet, Deep Lab, all kinds of stuff. So what we're going to use is just a UNet, which is a pretty simple, and well, it's a commonly used architecture. Okay, and you can see all the arguments that are available here. So we got our required arguments. You have to give it some data. You have to define a backbone to use. You have to specify pre-trained path. I guess these are all technically optional, but it's going to do something. And then pick a backend, and then you have some additional arguments here. Okay, so I'm going to move this over to my other screen because I might need that as I set stuff up. Okay, so let's look at our options. So this is going to be under Image Analyst and then Deep Learning. And what we want to do is train a deep learning model. So let's open that up. All right, so we need some input training data. So what it's going to want, I believe, let me go to my folder here. So I believe it wants the, well, let's actually look because I'm not 100% sure. Let's see what it asks for here. The folder containing the image, chips, labels, and statistics. Okay, so once our folder, and it knows, it tells you it has to be 3-band and has to be 8-bit. That's one of the issues with running these tools in Arc without using some of the more complicated environments with in code. It does limit your options. Like we can't use like a 4-band image, for example. But that's okay in this case because we basically do have an image that's an an image that's, you know, an 8-bit 3-band image. Okay, so I'm going to go into our topo data here, and then topo, let's see, we want to do topo DL data, and then processing, and then we want to grab, we're going to grab this KY chips 4, because that has our chips in there. And then as long as there's no issues, it should be able to read that that's some data that it can use to train from. While that's running, let's just have a look at some of these other settings. Okay, so the next option here is model type. So it's asking, like, you know, obviously what type of model you want to run. So if we do a drop down here, we can see there's a bunch of different options. What we're going to work with specifically is UNet pixel classification. So this is a semantic segmentation method, or pixel level classification. So we're definitely going to grab that. The batch size is going to be how many chips it runs through the network at once. You can't set this too high because it'll run out of memory, but we probably can get away with doing more than 2 since we use 256 by 256. So I'm going to change this to 12. I think that'll work. If it doesn't, then it would give us an error because of memory, and then we'd have to just set it down further. And then we can specify some arguments here if we want, and those are going to correspond to the arguments that are available here. Sorry, I moved up too far. So let me just click back on UNet here. So data, it's going to ask us for backbone, pre-trained path, and backend. So we'll look at that. But there are some additional arguments here. One that we can set is class balancing, mix up, focal loss, dice loss fraction, dice loss average. So there's a couple different things. One thing I want to do is, oh, look, added that is in. So we have class balancing is set to false, mix up is false, ignore class, we don't want to set anything there. That's useful if you have like a background class or a null class that you don't want to impact the weight updates or in the optimization. And then we have a chip size there. I'm going to set the dice loss, but I'm not sure, honestly, if this version is honoring it because it's not popping up. But according to the module documentations it supports, I'm going to set this at 0.3. So by default, it uses, I guess it's a probably binary cross entropy loss. But you can also use dice loss or a combination. So what this means is we're going to use dice loss and a combination of dice loss and BCE loss, where the BCE loss is rated at 0.7 and the dice loss is rated at 0.3. The next thing to set is a learning rate. Again, if you don't set this, it will try to come up with one using a learning rate optimizer. So I think it'll tell you that here. So the rate at which existing information will be overwritten with newly required information through the training process. If no value specified, the optimal learning rate will be extracted from the learning rate curve. So it basically integrates it uses a process that tries to optimize the learning rate. So I'm going to leave that. The default backbone here is ResNet 34. I'm going to drop it down to ResNet 18. It's a little smaller, so it'll train faster. Then I haven't downloaded any pre-trained weights, but if you wanted to start with pre-trained weights to do some like transfer learning, you could. And then lastly, we have what percentage to withhold to validate at the end of each epoch. And it's set at 10. I'm just going to up that to 20%. And I'm going to turn off freeze model. If you set the model to, if you freeze the model, that means that it's not going to update like the weights. It tells you here. So if it's checked, the predefined weights and biases will not be altered in the backbone of the model. If it's unchecked, the weights and biases in the backbone can be altered. So we're going to uncheck it. So what that means is instead of just updating weights at the end of the model and like the fully connected layers, it's gonna update. It can update weights across the entire model instead of just using the default ones. And I click stop when model stops improving. And it should be an option to set. Oh yeah, I missed this. So max epoch. So right now we have it set to where we'll iterate over the data up to 20 times. It might stop early though if it's not seeing any improvement. So I think that's probably fine. So I think that's set up. I'm going to hit run and we'll just let it initiate and see what happens. We won't obviously watch it because this is going to take a while. This will take at least several hours, and the amount of time it takes. Uh-oh, something's wrong. Oh, I didn't set an output location, so I'm just going to make a new folder in this directory folder, and we'll call this UNet Topo and Topo models. Okay, and that should add the correct extension for us there. Let's see if it wants. Okay, that should be fine. All right, so that's it. So let's hit run and see what happens. Okay, so we're back now and the model has completed running. So let's have a look at the output just to see what we ended up with. So you see here the elapsed time was 7 hours and 11 minutes. So it took a while to process, but that was 20 epochs, and also we had a pretty large set of training data, so that's really not that bad. And also the model weights were unfrozen, so that generally increases the training time. There was no messages, so there was no warnings or errors, as you can see, and then it did log here some information, so we can see the accuracy and the loss after each epoch, and then we have this overall here. So whenever you run one of these models, it's going to end up dumping everything in your folder that's included in the output. So one thing that's useful is this model metrics HTML file, which is a little report. So if we open that up, it opens up in your default web browser. And it'll tell you a little bit about the model. So we can see the backbone there, the learning rates that were used. This is the loss by epoch. The blue line is the training, and the orange line is the validation. So you can see that it actually leveled off pretty quick, and it doesn't seem like there's a lot of evidence of overfitting. And then we also have some class level metrics here, precision and recall, and F1 score for the background, and then for the mining class. And then lastly, it spits out and shows you some example output here. So this column is the input data, and then this is the prediction. As you can see, it lines up pretty well. So it looks like we're getting some decent looking output. Okay, so now that we have a model, let's actually use it to to predict to a new data set. Okay, so what I'm going to do is, just to avoid any confusion, just turn this stuff off. Let's find another topo map. And just to find something that's pretty different, we're going to go into a different state. So I'm going to grab one from Virginia now. Let's see what this last one looks like. And we'll zoom over to that layer. Okay, so there's a good bit of mining in this scene. So let's see how it does when it's predicted to this. Okay, so to actually use our model, we want to pick the correct tool here. So you can see there's classify objects, classify pixels, compute accuracies. What we're interested in is classify pixels because this is a semantic segmentation problem. Okay, so next thing we need to do is give it the data. So this is going to be our new data, and we'll just let it write to the default there. And then we need to give it a model definition file, and that's going to be part of the product that we got. So I believe that's this one. Let's see. And then that'll take a second to load. And as you can see here, it already auto-populates with some parameters. So one thing, just a couple notes here, the padding is useful. Basically that creates a little bit, so it's been shown that the edges of the image chips sometimes get predicted at a more poorly than the center. So basically what this means is the outer rows and columns 64 are not going to be included in the output. It's going to use some overlap. It's going to process at the same size. It's going to predict a background, and also the class will get like a 0, 1 output instead of just the ones. It says it's going to run 4 chips at a time. So since the training process happens at the scale of image chips, then the inference or prediction process has to happen also, or has to happen on image chips also. So one thing nice about doing this work inside of ArcGIS is it's going to do all that for us in the background. So it's going to break this image up into overlapping chips, do the processing on the chips, and then reassemble the image for us. So we don't actually have to do that ourselves manually in some type of like loop or something. Okay, so let's just leave the default settings there, and we'll click run, and we'll see how long it takes us to get an output here. Alright, so I was running this process, and it actually was taking a fairly long time. So I think the issue is that it was trying to run this on the CPU as opposed to the GPU. So I'm going to restart this process, but I'm going to go into the environments and tell it that I wanted to specifically use the GPU for this. So we're going to go down to under the environments options here, and processing type, we're going to change it to GPU, and the GPU ID here is 0. It's this index, so if you have more than one GPU, you can pick one. I only have one, so it's going to be the index 0 here. That should be my 2080 graphics card. Okay, so if I'm going to change that to the GPU processing, I believe this should fix the issue. So I'm going to just add a 2 on the end just in case it partially generated that, and we'll reinitiate this and see if it speeds it up. Okay, so after switching over to using the GPU, this actually executed pretty quick. So if we look in here in the messages here, we can see that it took a little over a minute to execute. I'd let it run on the CPU for about 10 minutes before I killed the process. So again, you can see that actually speeds it up a good bit. And all the blue areas here is what ended up as our prediction. I just changed the color there. So if we zoom in, we can see it looks like it did a pretty decent job. Some of this like tailings symbology wasn't really included in the other data set. That's why it's not getting picked up. This is kind of a unique, but it did pick up the pattern that we trained on. So I mean, generally speaking, I would say that this did a pretty good job. Generally, this is a bit of an art and a science. You can see there's some false positive there, but for the most part, it looks like it's doing a decent job. So what could be done to potentially improve the prediction? So first off, you could train using more training data if you have that available. You could fiddle with the settings, such as using the dice or using class balancing. If you play with a lot of these settings and you're still not getting what you want, it may just be that the problem that you're trying to investigate is actually fairly complicated, and it's just a difficult classification problem. Another option is that you could try to do some more precise or specific adaptations of the training process or the training data or whatnot. In that case, you're probably going to need to switch over and do some work in a more code-based environment. And we'll look at that in some other videos when we investigate doing these types of things in PyTorch. Okay, so in this series of videos, I showed you how to generate training data, use that training data to train a model, generate a trained model, and then use it to infer onto new data. And this was again done in the Arc environment with little to no coding, though I did show you how to loop through large numbers of data sets to generate chips. Okay, so there will be a few other examples and with some different use cases, and I hope that you found this useful.